So today we're combining information that has to deal with ideal solutions and chemical potentials. So really synthesizing knowledge from the last few lectures. To start with, what we're going to do, and we're going to see that Raoult's law plays a critical role in how we actually make that link. What we're going to start with is just kind of analyzing a pure substance, and we're going to go through a process that feels real familiar. If I have this pure substance, a vapor pressure can be established. All right. Once that vapor pressure is established, there's no net movement between, all right, the vapor to the liquid phase or the liquid to the vapor phase. Right. Just have a pure substance, a vapor pressure is there now. There's no net movement. There still is movement, but the system is at equilibrium. We know from a chemical potential standpoint that when a system is at equilibrium, the chemical potential of the choices it has to make are the same. So in the context of this, the chemical potential to be in the liquid phase is the same as the chemical potential to be in that vapor phase at equilibrium, right? Until you reach equilibrium, these two might be different, and then the lower one dictates what's favored, but once you're at equilibrium, we know that they're equal to each other. Well, last time when we were discussing this vapor phase, we kept on referencing that we treat it like an ideal gas. So can we come up with a chemical potential formula for that vapor phase, which is an ideal gas? Because if we can, then at equilibrium, that expression that we build is also equal to the chemical potential of the liquid, right? So by knowing chemical potentials of gases, we can actually infer chemical potentials of the pure liquid. What does that process look like? And again, I referenced it before, but this is going to feel familiar. Well, if I look at a natural variable relationship that we derived, which is how G and P relate to each other, right, in the context of an isothermal process, we have this starting point that we actually analyzed before for Gibbs energy. Now, what we're after here is information about chemical potential. So if you remember how we turn chemical potential into Gibbs energy or Gibbs energy into chemical potential, it's all about introducing an N. And I know that G is molar Gibbs energy. So if I divide both sides by small n, then I can write this formula here. Now I can rewrite this. As soon as I see a molar Gibbs energy, I know that that is actually a mu. That's actually a chemical potential. So d mu dp at a constant t is the same as molar volume. Now, why are we focusing in on G for this process? We kind of look at these like as situations that are open to the atmosphere and that are at a constant temperature. G matters because we're eventually going to be referencing a certain set pressure and a certain set temperature, isobaric and isothermal conditions. So that's when chemical potential really matters for us as chemists, and so that's why we're focusing there. This differential equation, we know how to solve. We know that we can take, all right, the P to the other side, and we know that this is only valid for isothermal situations. We can then integrate both sides between a P1 and a P2. Okay. We know here we can actually simplify this integral further because remember that this V that we have is an ideal gas V. So you can rewrite it as RT over P. We also know that we're dealing with an isothermal situation, so the R and the T will be able to pull out of that integral. So what we're left with is math that hopefully feels familiar, right? Over here, I'm going to write this as mu of P2 minus mu of P1, right? Over here, I pulled out the RT. I have a dP over P. So I'm going to have an RT natural log of P2 over P1. Now we're going to make some changes here. We're going to just kind of add information because eventually we're going to be using expressions and talking about solutions. But remember what we're talking about right now. Right now we're talking about the chemical potential up here in this ideal gas vapor. And if we can figure out what that is, that's the same as the chemical potential down here. So what I'm going to do is just a bit of rearranging and then a bit of relabeling. Okay, so please pay attention to what we do here. I'm just going to call P2 P. All right. And what I'm going to do, so I'm going to write down here, P2 equals P. So what I'm going to do is, because we want this to just be a general formula for like any pressure, that subscript 2 doesn't really matter as much once we get to the analysis part here. All right. Because what we're going to do for P1 is just like before, we're going to pick our standard pressure. Remember what these P's are. These are pressures up here in this vapor phase. These are the vapor pressures, okay? We're going to do a standard, though, vapor pressure of 1 bar, just like we would for any ideal gas standard. Instead of writing this as mu of P1, I'm going to bring it to the side, right? Or instead of writing it as mu of P1 or writing it as mu of 1 bar, we know that when we're analyzing, all right, things at standard conditions, we use the superscript not, all right? So this means, all right, we're now analyzing this mu of P1 under standard conditions. We're going to have plus RT here, the natural log. Okay, so what am I going to do here? P2 becomes P, and P1 becomes 1 bar, all right? So the P1 kind of goes away because this P inside here, as long as I know that I'm referencing bar of pressure, is going to be divided by 1 bar. This P right here is the same P there, and it's in bar, okay? So this is the situation describing the chemical potential of this vapor. And like I said, we kind of did this before. We might have written this as over P naught, right, when we did it for Gibbs energy, but I'm even going to just leave that out because that gets cumbersome to keep writing. And we know P naught is there. We know that 1 bar is there, but dividing by 1 doesn't change mathematically what this value is inside the natural log, all right? So this describes the chemical behavior of the vapor, but at equilibrium, this vapor chemical potential is the same as the liquid chemical potential. And I know I said that a bunch, but it's important. The other thing we're going to do here is because we're eventually working towards information about solutions, right? We're going to remind ourselves of a couple things. This is the chemical potential for the vapor. So we're going to use that as a superscript indicator. This is mu for the vapor. That depends on the pressure, okay? This is also, right, for a pure situation. Notice this is not a solution yet, okay? So what we're going to do is we're going to say this is the chemical potential for a pure vapor pressure, right? And over here, right, this P would also get a star. So we're going to use this superscript star to indicate that we have pure species, or that we're looking at the chemical potential of pure species. Right? The mu doesn't get a star because whether the mu was for a pure species or for a solution, the ideal gas standard is always the same, and that kind of makes sense. Once you establish a standard, it just is the standard. So we don't need a star there, but we do need to signify that this work, it all came from the idea that we were looking at the pure situation first. All right, so we're going to call this a mu vap star, and we're going to call this a P star. All right. Now, let's go ahead and let's keep this here, but let's focus in on a solution now. So let's put some red particles here, right? And what do those red particles do? Those red particles also leave the surface, and we can draw a double arrow here. That's a terrible double arrow, but you know what I'm writing. We can draw a double arrow here that shows, right, that a vapor pressure is established between, right, the red particles in the solution now and the red particles in the vapor, all right? So what changes about this analysis, right, for this red particle or blue particle behavior? Well, nothing really changes, okay? So if you kind of think about what's happening here, we would still look up in this vapor phase, and how would we treat it? We would still treat it like we have ideal gases. The only thing that's really different here is that there's a lot of chemical potentials. There's essentially 4 chemical potentials we can look at. There's the chemical potential for the blue to be in the solution, the chemical potential for the red to be in the solution, the chemical potential for the blue to be in the vapor, right? Or the chemical potential for the red to be in the vapor, okay? At equilibrium, those chemical potentials are equaling each other out, okay? So let's just kind of take a look at what changes about our thought process. Well, nothing really. If I look now at mu to be in the vapor for a species here, if I treat it like an ideal gas, the entire process of coming up with this formula is exactly the same. All right? The only thing that's different, and the main difference that sort of applies eventually to Raoult's law is am I really dealing with a pure substance now? And the answer is no. This is still an ideal gas vapor. We can still go through that partial derivative identity, but I'm not going to put stars here now. All right? I'm not going to put stars there. And the reason I'm not going to put that there is because there's blue things and there's red things that are intermingled to each other. So the pure vapor pressure isn't necessarily the vapor pressure that you find in the solution. And that should kind of click for what we said with Raoult's law, right? We know that this vapor pressure is actually lower, okay? So hopefully that makes sense here. Nothing really changes. So even in the solution, we have similar forms for the chemical potential. Now, Raoult's law was all about comparing pure vapor pressures to vapor pressures in solutions, and that's going to be our next step. So let's remember what we have here. We have this mixture, and now we kind of understand what the chemical potentials look like. And I'm just going to kind of write this out one more time. For the solution, let's say we're looking at species 1. So let's call our red species 1. Now, whatever we say about species 1, we're going to be able to say about species 2 as well. I'm going to try to abbreviate solution like your book does. Your book uses SLN, but I keep using the superscript N underline. Just kind of get used to that. For that solution setup, right, for species 1, the chemical potential to be in the solution, right, is equal to the chemical potential, all right, to be in the vapor phase, okay, for that species 1, okay? We also know that the chemical potential to be in the vapor phase looks like mu naught plus RT, the natural log of P, right? Now this is, again, species 1, so I'm going to put a subscript 1 there. Now for species 1, we also know that if we were talking about pure 1, all right, pure 1, the chemical potential to be in the liquid for pure 1, right, is the same as the chemical potential to be in the vapor for pure 1, which looks like the same standard plus RT, the natural log of P1 star. Okay, so everything about this video led up to this point where we can make these declarations about the chemical potential of the solution being equal to the vapor chemical potential at equilibrium, and then having a function to analyze, right? Notice they're the same except for the pure. We make sure we're talking about a liquid and not a solution, and we put this star there. Now what we're going to do here, critically, is we're going to focus right here, okay, and here. Remember, these are all equal to each other, but those are the parts of the equations that we're going to focus in on, and we're going to subtract. And if I subtract right here, I'm going to get mu for the solution for species 1 minus mu for species 1 as if it was in a pure liquid is equal to, once I do this subtraction here, remember what we said about this mu? It's the same mu. It's the same standard. The vapor, right, has the same standard no matter if you're talking about pure vapor or vapor in a mixture. They're all ideal gases analyzed at 1 bar. So when I do this subtraction, the mu naught goes away. I'll be subtracting natural logs on this side. So I'm going to write this as RT, the natural log of P1 over P1 star. All right. Now, where have we seen P1 over P1 star before? All right. Now, just kind of notice, okay, so sorry before I get ahead of myself. This right here is an incredibly powerful statement. It tells us, all right, how the chemical potential changes as you make a solution, right? And if I look over here, the main things to kind of realize here is that if I can figure out what your vapor pressure is in the solution and what your pure vapor pressure should be, all I need to know is the temperature to figure out how the chemical potential has changed, all right? Now, if you have an ideal solution, this P1 over P1 star, we actually know how to analyze in an important way. Raoult's law tells us that P1 is equal to chi1 P1 star. So incredibly, right? Maybe you're not excited about it as I am, or as excited about it. Chi1 looks like P1 over P1 star. So incredibly, if what I look at here and the importance of this is all I need to know now is a solution's concentration. Now I have to know it in mole fraction, but that's something we can get to or work towards, all right? But if I know this concentration, notice, right? If something follows Raoult's law, P1 over P1 star, that ratio is chi1. So then this equation for ideal solutions, right, for ideal solutions ends up being, right, the equation that we had blued off before, like in the blue box, that's just a true equation. It just works for any vapor pressures. But if the vapor pressures follow this concept, if they're ideal vapor pressures, this equation for ideal solutions becomes, right, RT natural log of chi1 on the right-hand side. Okay, so I've linked, right, solution information to, and solution concentration information to chemical potential information, right? A real incredibly important idea, right? So realize the first thing that was blued was true for anything. If your P1 follows Raoult's law, now we can replace that fraction in there with chi1, right? So this is a very powerful tool, right, that we then can go and use to analyze the thermodynamics of our solutions. Now, before I conclude this video, I picked one. What changes about this analysis for species 2? Well, nothing, okay? So in that vapor phase, there's both red and blue. If you look at the blue, absolutely nothing changes except the subscript. So what we can do is we can make this a little bit more general, right? We can turn these into I's. Now remember when this is true, all right? I know I said it a bunch. This is true for ideal solutions only. Because remember, for ideal solutions, that's when Raoult's law applies and you can make that a chi. If we don't have Raoult's law applying, right, we'll have to do something else in there with that fraction to maintain this form that we like, right? To maintain this form that we like, okay? So that's it for this video. So try to make sure you can reproduce this derivation. We're now going to use these to start to pick apart thermodynamic properties of ideal solutions, and we'll be doing that next time.